class. Today we will discuss on the following objective. The objective would be to define the strain compatibility equations. So we have studied the what are the equations of the equilibrium. In this lectures we will study about the strain compatibility equations. So we will get the different sets of the equations. First sets of the equations we will get from the equations of the equilibrium, and second sets of the equations that needs to be satisfied is through the compatibility conditions. So we will study what does these equilibrium equations and what does these compatibility conditions do to our systems, and what does it has, what are its importance. So the equilibrium equations sets the externally applied loads equal to the sum of the internal elemental forces at each and every small points, or we can say that at all the joints or the node points of any structural systems. They are the most fundamental equations for any structural analysis and the design. The exact solutions for our problems in the solid mechanics requires that the differential equations of equilibrium for all these infinitesimal small elements within the solid must be satisfied. So these equilibrium equations are the fundamental laws of physics and cannot be violated within the real structural system. So if we are looking for a uniquely defined solution, then it is very compulsive to define these sets of equations and to satisfy these sets of the equilibrium equations. Compatibility conditions also needs to be satisfied. However, if one has a choice between satisfying the equilibrium or the compatibility conditions, one should go for the equilibrium based solution, because for a real non-linear systems equilibrium equations are generally satisfied in the deformed positions, and many real structures do not satisfy the compatibility requirements. That compatibility requirements caused due to the creep can be due to the joint slippage, or it can be due to the incremental constructions and the directional yielding which can occur in a continuum. Compatibility requirements are that for any continuous solids we have defined the strains as the displacements per unit length, and to calculate the absolute displacements that are occurring at a point we must integrate the values of the strains with respect to a fixed boundary condition. So in the problem the different boundary conditions can be given. It can be fixed boundary conditions, it can be simple support boundary conditions, or the boundary conditions can be in the forms of the roller. Then these integrations can be conducted over many different paths. A solution is compatible if the displacement at all these points is not a function of the path we choose. Therefore, displacement compatible solutions involves the existence of a uniquely defined displacement field. So in order to get a unique solutions in terms of the strains, first we need to define the displacement field. If we know the displacement field that are in the forms of u, v, w, which are the displacements acting in the x directions, displacement acting in the y direction, and the displacement acting in the z direction, then we can define the displacement field, and consequently we can calculate the values of the strains. The strain compatibility equation. So the case one is that for a 3D continuum, this means that we are working in the three-dimensional Cartesian coordinate system with the coordinate axis being x-axis, y-axis and z-axis. If we know the three displacement components in the Cartesian coordinate system, the three displacements are the displacement in x directions represented by u, displacement occurring in the y direction represented by v, and the displacement occurring in the z directions represented by w. Then this three displacement components can be represented in a particular functions. This function is in the forms of x, y and z, and this particular functions is known as the displacement field. So in such a case, in the first case, if we know the displacement field, we have a uniquely defined displacement field, and we are interested in calculating the six strain components, then these six strain components can be calculated using the six strain displacement equations that we know. So these strain displacement equations are, first three sets of the strain displacement equations are for calculating the longitudinal strain or the normal strains, and the next three sets of the equations are the equations for calculating the shearing strains. So what does these strain equations do? It relates the strain with that of the displacement that are acting in the x direction, y directions and z direction. So if we are interested in calculating the values of epsilon xx, then how we will be calculating? We will be partially differentiating the displacement that are acting in the x directions with respect to x. If we are interested in calculating the normal strain or the longitudinal strain in y direction, we will be partially differentiating the displacement that are acting in the y direction represented by v with respect to y. And next would be, if we are interested in calculating the strains that is acting in the z directions or the normal strain, we will be differentiating the displacement that is acting in the z directions, which is w with respect to z. It is z, it is by misprint, it is z, not x. So these are the three different values of the normal strains that are we can calculate if we know the displacement that are acting in the x directions, y directions and the z direction. Similarly, we can calculate the values of the different strains. The strain gamma xy, which is again partially differentiating the displacement that is acting in the x directions with respect to y, displacement that are acting in the y directions with respect to x, which is equal to 2 epsilon naught xy. Similarly, we can calculate the shearing strain gamma yz is equal to partially differentiating the displacement that is acting in the y directions with respect to z, partially differentiating the displacement that is acting in the z directions with respect to y, which is equal to 2 epsilon naught yz. Similarly, we can calculate the values of the shearing strains gamma xz by partially differentiating the displacement that is acting in the x directions with respect to z, and partially differentiating the displacement that are occurring in the z direction with respect to x, which is equal to 2 times epsilon naught xz. All these equations we have earlier derived. All these equations, which are known as the strain displacement equation for calculating the values of the normal strains or the longitudinal strains or and the shearing strains. Case 2. In the previous sections, we know the displacement and we were interested in calculating the values of the strains. Over here, if we know the 6 strain components and we need to find out the 3 displacement component, then the solution will not be unique unless a set of the equations being enforced on the strain components, and such sets of the equations that are enforced are known as the strain compatibility equation. So we will derive the what are the strain compatibility equations. Altogether in 3D space we have 6 strain compatibility equations. So for calculating the strain compatibility equation, it is the relationship between the strain that is acting in the x direction, strain that is acting in the y directions, and a strain that is acting in the z direction with the corresponding shear strains that is acting on a particular plane one by one. So first of all, we will derive an expression for the strain compatibility equations in the xy plane. For that, what we need to do, we know we can partially differentiate the strain that is acting in the x directions. Then what we know, this strain epsilon xx is how much? It is partial derivatives of u with respect to x. If we differentiate it, we will finally get the solutions in terms of the displacement. We will get del q by del x del y whole square, which is the differentiations of displacement in x directions. Similarly, we can do the same thing, which is the double partial derivatives of the strain that is acting in the y direction with respect to x. Now we know the values of epsilon naught yy. What is epsilon naught yy? It is del v del y. So if we differentiate it, we will get the following equations, which is del q v del x square dy. So if we add these two equations on the LHS, if we add this equations with this equations, which is shown over here, so this equations is this and this equations is this, then finally we will concludes that we have arrived to a following equations. And rearranging these terms, now this terms is a term for the shearing strains that is acting on the xy plane. So we can conclude that this can be replaced by epsilon naught xy. So this one is the first strain compatibility equations in the xy plane. If we carry out the similar formulations what we did for the xy plane, for the yz plane, we will arrive to this strain compatibility equations which is in the yz plane. And similarly, if we carry out the similar formulations, we will again get a strain compatibility equations that is in the xz plane. So what does these strain compatibility equations does? Here we can see that these equations, what does it do? It relates the values of the normal strains, so normal strain in y directions, normal strains in z direction, to that of the shearing strains that is acting on the yz plane. Similarly, for the xz plane, what does it do? It relates the strain that is acting in the x directions, strain that is acting in the z directions, to that of the shearing strain that is acting in the xz plane. Similarly, for the xy plane, what does it do? It relates the values of the strains that is acting in the x directions, relates the values of the strain that is acting in the y directions to that of the shearing strain that is acting in the xy plane. So we have arrived to three different strain compatibility equations which relates the values of the normal strain or the longitudinal strain to that of the shearing strain. The next objective would be to relate the values of the strains in the xz plane and the values of the shearing strain in xy plane with the stresses that are acting in the x directions and the stresses that are acting in the y direction. In order to do this, we will differentiate it with respect to x in order to get an equations. So we can replace epsilon naught xz by the this formulations. Epsilon naught xz is equal to 1 by 2 multiplied by partial derivative of u with respect to z, plus we can replace epsilon naught xy by partial derivatives of u with respect to y plus partial derivatives of v with respect to x. So this represents epsilon naught xz represents the following these two quantities multiplied by 1 by 2, and epsilon naught xy represent these two quantities multiplied by 1 by 2. If we finally carry out these formulations, we will finally reach to an equations of this forms, which is partial derivatives of strains in x directions that is done with respect to y and z, partial derivatives of strain in yz plane with respect to x square. If we finally rearrange these terms, the x directions LHS terms and to that of the RHS term, we will finally get the following sets of equations. So this one is again the fourth strain compatibility equations. If we carry out the similar formulations what we did over here, to carry out the relationship between, if we carry out the partial derivatives of xx with respect to y and z, similarly we will get the equations, other sets of the equations. The other sets of equations is partial differentiating of epsilon naught xx with respect to x and z, which is equal to partial derivatives with respect to y to the following different strain quantities, shearing strain quantities. So these are the different shearing strain quantities: epsilon naught yz, epsilon naught xz, and epsilon naught xy. Similarly, if we carry out the similar formulations, we will get the values of the normal strains, which is double partial derivatives of epsilon naught zz with respect to x and y. We will get partial derivative with respect to z, which is multiplied to partial derivatives of epsilon naught yz with respect to x, partial derivatives of shearing strain xz with respect to y, and partial derivatives of epsilon naught xy with respect to z. So we have derived all the 6 strain compatibility equations. So apart from this, apart from other sets of the equations, these equations also needs to be satisfied if we are interested in finding a unique solutions. So the learning outcomes of these sessions are, so we have derived the 6 different strain compatibility equations. So apart from the other sets of the equations which are the equilibrium equations, these 6 sets of the strain compatibility equations also needs to be satisfied. This is all for this sessions. We will meet you in the next sessions. Thank you.